Next, we'll look at the region of convergence and stability of the Z-transform. Before we start, we will review some important concepts. First, we'll look at the convergence of sums, since the Z-transform is defined as an infinite sum. For all summations, we can say that it converges if and only if the result of the summation is less than infinity. Since we can represent some important transforms as geometric series, we can show that the sum can be written in closed form as 1 over 1 minus the expression we are summing over. This expression may only be used when the convergence condition is met, which is when the magnitude of b is less than 1. Next, we'll look at poles, which are defined as the values where a function goes to infinity or is undefined. Many z-transforms result in rational functions of the form f of x equals p of x over q of x. For these functions, the poles are located at the zeros of the denominator polynomial q of x. Recall from the previous video that the magnitude graph of a DTFT repeats every 2 pi and has a radius of 1 in the z-domain. The equation of the z-transform is in polar form, which creates a circle in the z-domain. If we take a discrete time pulse and calculate its DTFT, we get this graph, which has a periodicity of 2 pi. If we calculate the z-transform, we get this graph, with the imaginary part of z on one axis and the real part of z on the other axis. The unit circle is inside the region of convergence. With r equals 1, the DTFT is the unit circle in the z-domain. If we know that the unit circle exists in the z-domain, we know that the DTFT exists. And when talking about system analysis, a system is stable when the unit circle is in the region of convergence. If we were to compare the z-transform with the DTFT through their constraints, we would find that for the DTFT, the signal must be absolutely summable, since it only exists at the unit circle. So if we took the transform of this exponential signal, we would get no spectrum. For the z-transform, however, the signal multiplied by the inverse of r must be absolutely summable, which means there are values of r that make it summable. Now, if we took the transform of this exponential signal, we get this graph, which has the unit circle outside of the region of convergence. Taking a closer look, what is in a z-domain graph after doing the z-transform? We have the region of convergence, which is all of the values of z which make the equation converge. We have the radius r and angle omega, which is used to locate any of those points. And we have the imaginary versus real part of z. We also show the unit circle so that we can determine the stability of a system. Going further, there are 3 types of z-domain graphs corresponding to 3 cases of convergence. In case 1, the convergence is outside of the circle. In case 2, the convergence is inside of the circle. And for case 3, the convergence is between 2 circles, or a ring. And these are their graphs. To understand all 3 cases, we'll look at a few examples. For case 1, let's look at the transform of the causal exponential. Plugging into the definition, we get a sum from minus infinity to infinity of the exponential times z to the negative n. After applying the unit step and rearranging, we see that the sum is also equal to the geometric series of a times z inverse. Applying our convergence restriction of a times z inverse less than 1, we can use the closed form expression, which means that the z-transform is equal to 1 over 1 minus a times z inverse, which is only valid for z greater than a. For z less than a, x of z does not converge. And this is, if we were to plot it out, this is the graph, where the radius of the circle is a, and everything inside does not converge, and everything outside does converge. For case 2, we'll look at the anticausal exponential. Plugging into the definition, we get a sum from minus infinity to infinity of the anticausal exponential multiplied by z to the negative n. Applying the unit step and rearranging, we get this sum, which is from minus infinity to minus 1, which looks similar to the geometric series form, but has incorrect bounds. To make the bounds equal, we can apply a simple variable change to get it from 1 to infinity, and subtracting out the n equals 0 term, we can get it into the correct form. Now, applying the restriction of A inverse Z less than 1, we can use the closed form expression and find the Z transform is equal to 1 over 1 minus A times Z inverse, which is only applicable for Z less than A. If you compare this to what we got for case 1, or the causal exponential, it's the exact same expression, but the only difference is the region of convergence, which means that Z transforms are not unique, and that to fully understand them, you need the region of convergence and its expression. If we were to plot this, we get this graph, with the circle being a radius of A, everything outside of the circle does not converge, or Z greater than A does not converge. Everything inside the circle, or Z less than A, does converge. Case 3 is a combination of case 1 and case 2, so we'll look at a causal exponential minus an anti-causal exponential. Using our previous derivations, we can come up with this expression, which is only valid for Z greater than A and Z less than B, or for Z in between A and B. Plotting this, we get this graph, where the outer circle's radius is B and the inner circle's radius is A, and the region of convergence is in between those two circles. Looking at properties of the region of convergence, first, we have that the ROC cannot contain any poles. That's because poles are defined as being undefined. Second, right-sided signals converge outside of the circle, which is what we saw in case 1. If you go back to that example, you'll see that the region of convergence is on the exterior of the outermost pole. Third, we have left-sided signals converge inside of the circle, which is case 2. If you go back to that example, you'll see that the region of convergence is inside the innermost pole. 4, we have that two-sided signals converge within a ring, or case 3, which we have the region of convergence being in between the two poles. Finally, we have that finite length signals converge everywhere except possibly z equals 0 and or infinity. To understand this, let's look at an example, let's look at a delay signal. If we plug this into the definition, we get that the z transform of the delay is z to the negative n naught. Just by inspection, we can see that if n naught is greater than 0, z cannot equal 0, and if n naught is less than 0, z cannot equal infinity, otherwise these would be poles. Plotting this out, we get these two graphs. Although they may seem like different cases, they are actually the same cases as case 1 and case 2. It's just that if for n naught greater than 0, the radius of the circle is just 0. And for n naught less than 0, the radius of the circle is just infinity. Next, we'll compare the regions of convergence of the Laplace transform with that of the Z transform. These are the three graphs of the regions of convergence that we came up with in this video for the Z transform. These are the three corresponding graphs of the regions of convergence for the Laplace transform. The black lines are the boundaries of stability for each transform. For the Z transform, that's the DTFT, and for the Laplace transform, that's the Fourier transform. Finally, we'll do some examples to reinforce our understanding of the concepts presented in this video.
In this example, we'll be taking the z transform of our impulse. And so we define our impulse with some delay, and when we use the z transform definition to find our transform, we know that multiplying the impulse by this function z to the negative n is nothing but our function defined at where our impulse is, which in this case is n naught. And so our z transform is defined as z to the negative n naught. And so when we look at when this term exists, we look at two different cases, when n naught is a positive value and when n naught is a negative value. When n naught is a positive value, then we know that this term becomes z to the negative n naught, or 1 over z to the n naught, and we know that z cannot equal 0 because 1 over 0 is an undefined value. Similarly, if n naught is a negative value, then we'll have a term z to the n naught, and that will not exist for when z equals infinity. So then we can define our property for the z transform of an impulse as z to the negative n naught where our region of convergence exists for every value of z when n naught is positive, except for z equals 0, and it exists for every value of z when n naught is negative, except for when z equals infinity. In this example, we'll be observing the z transform of a non-causal unit step. Remember that non-causal just means in the time domain it's a left-sided signal, or it only exists for negative time values that are not greater than or equal to 0. And so if we flip and shift our unit step, we can get it as a non-causal term. And finding our z transform, we can take advantage of the fact that it doesn't exist for every n value greater than or equal to 0, and so this term disappears and we have it in the form of this summation where it's a negative time sequence, and we don't have a property to solve a summation of a negative time sequence. We want it in the form of a positive time sequence where a to the n equals a over 1 minus a. And to do that, we take advantage of the time reversal property, and we're able to get it in the form of z over 1 minus z. And observing our region of convergence, we can start with our general statement that our region of convergence has to be greater than 0. And observing our pole, we can say that 1 minus z has to be greater than 0. And isolating for z, we can get the statement that our region of convergence z has to be less than 1. And so what does that mean? If we have a circle of radius 1, our region of convergence exists for every value inside that circle for our non-causal unit step. And for our last signal, the causal exponential, of course, opposite to non-causal, we know that causal should mean that it's a right-sided signal in the time domain, which also includes the value 0. And we'll be observing the exponential that's decaying over time, so our alpha will be in between 0 and 1. And so when we use the z transform definition to find our z transform, we can get it in this form, where we know that's a geometric series and it's defined as such. And so our z transform of a causal exponential is 1 over 1 minus alpha z to the negative 1. And so when we observe our region of convergence, we can again start with our general statement that our region of convergence has to be greater than 0. And observing our pole, we know that 1 minus alpha z to the negative 1 has to be greater than 0. And isolating for z, we get the statement that our region of convergence has to be greater than alpha. And so what does that mean? If we have a circle in our z-domain of radius alpha, our region of convergence is everywhere outside of that circle.